Hello and welcome back. This is the second part of the module on non-woven textiles. In this non-woven textile module, we will be looking into the bonding technology, a brief introduction about the bonding technology. In web bonding, the fibers are consolidated to produce felts. Bonding on the non-woven web is the primary factor in determining the non-woven fabric strength, integrity, flexibility, porosity, density, and softness. Fiber characteristics such as the fiber type, shape, geometry, location within the fiber felt mass, and the degree of bonding. Non-woven web consolidation bonding can be brought about by the mechanical, chemical, solvent, and thermal means. Bonding is generally carried out as a sequential operation in tandem with web formation. However, it may also be carried out as a separate and distinct operation. In choosing the web consolidation method, the desired product properties followed by economy, versatility, strength, softness, and primary absorbency needs are to be taken into account. The techniques available for web bonding are largely classified as the mechanical process. Under the mechanical process, there are two variations, which is the needle punching and the hydro-entanglement techniques. And then the thermal bonding process, which includes hot calendering, belt calendering, through air bonding, and the ultrasonic bonding, radiant heating bonding, etc. And the chemical bonding process involves saturation, spraying, printing, foaming techniques. Now we'll get into the details of the mechanical bonding process, that is the needle punching technique. The needle punching industry around the world is an exciting and diverse trade and enjoys one of the greatest success. In this method, web bonding or consolidation is brought about by a repeated insertion of the barbed needles into the preformed dry fibrous web, which is also called as a bat, which is unbound, thick and voluminous, either from one side or from both the sides. This consolidation of initially arranged staple fibers in different orientation, it could be cross, parallel, or perpendicularly, is brought about by interlocking of fibers in the Z direction. Needle punching is carried out on needle looms. The barbed felting needles are repeatedly passed in and out of the web. The web passes through two plates, namely the web plate on the bottom and the stripper plate on the top. Holes are located in each plate, and it is through these holes the needle carry bundles of fibers through the bed plate holes. The stripper plate strips the fibers from the needle so that the material can advance through the needle loop. The performance characteristics of the needle punched non-wovens largely depend on parameters such as the nature of fiber, aerial density of web, penetration depth of the needle density, and the number of passages. Needle is the heart of the needle punching machine. Selection of suitable needle is very essential for getting good quality non-woven fabrics. Needles are generally triangular in cross section and carry barbs, and the dimension of the barbs and the relative arrangement depend on non-woven application and machine operation. Needle gauge is defined as number of needles that can be fitted in a square inch area. Thus, finer the needle, higher the gauge of the needles, whereas coarser fibers use low needle gauge. The more needles penetrate the web, more dense and stronger the web generally becomes. Needle punched non-woven find extensive application in civil engineering, railways, and geotextiles, to name a few. From the schematics and figure which shows the operation of the needle punching machine, you can see the loose fibrous web being fed by the conveyor into the needle board, and you can see the stripper board as well the needle board 2, needle board 1 and needle board 2. And as the needle board penetrates into the fibrous web, drawing the fibers from the top layers into the Z direction, it goes through the fibrous web and consolidates the web by carrying a few fibers and interlocking the fibers across this direction. And as they pass through, it is being delivered from the roller. So this is how the actual needle crossing actually is being carried out. The second mechanical technique which is being enormously used is the hydro-entanglement. In this method, web bonding or consolidation is brought about by subjecting the web, that is a loose fibrous material, it could be both synthetic or natural, supported by a conveyor belt to high pressure fine water jets. Here fluid forces is used to lock the fibers together. As the water jet strikes the web, the fibers get deflected and the agitation within the web brings about the fiber entanglement. This process is accomplished in a hydro-entanglement or spun-laced machine. Important fiber characteristics essential for this process is fiber hydrophilicity and flexural rigidity of the fibers. Coarse fibers with high flexural rigidity compared to fine fibers would require more hydro-entangling energy to have similar bonding. The fibrous web is supported on the surface with randomly distributed holes, and the high velocity water jets are directed towards it. As a result of the high pressure jets, entanglements among the fibers are introduced by the combined effect of incident water jets and the turbulent water created in the web, which twists fibers together, fibers around each other, forming an integrated structure. One problem associated with hydro-entangled nonwoven quality is related to the jet marks, which spoils its aesthetic appearance and also reduces the mechanical performance. Most of the de-energized water is drawn through the permeable membrane for reuse. The consolidated web is further dried to remove the water. The performance characteristics of the hydro-entangled nonwovens largely depends on parameters such as fiber properties, web property, and jet and forming wire geometry. Hydro-entangled nonwovens have a wide range of applications such as medical dressings, automotive fabrics, linings, clothing, personal care, household wipes, etc. Schematics below shows the working of a hydro-entanglement technique. You can see a circular frame which is being vacuumed, over which the fibrous web is passed through, and the high pressure water jets are normal to it. As the water impinges on the fibrous mat, you can see the consolidation happening, and the excess water is being drawn through the vacuum at the bottom. The next technique of fiber consolidation is the thermal bonding process. In the past few years, the growth of thermally bonded webs have steadily increased. The viability of this process is rooted to its price advantage and ability to address demanding quality requirements. Better web formation technologies have made this process more viable for both disposable and durable nonwovens. The main requirements of the binder polymer are good melt flow characteristics, good adhesion characteristics, low melting point with respect to the carrier fiber. Binders for thermally bonded nonwovens may be in the form of binding fibers. Both single and bicomponent fibers are most commonly used as bind fibers in thermal bonding nonwoven. Binding powders, sometimes powdered polymers, are also used when a lightweight, soft and open structure fabric is required. Binding web. An open structured thermoplastic fabric with low melting point is positioned in between two layers of the web, and when pressed together, the calendar rolls, the fabric melts, bonding the webs together. The next technique is hot calendering. There are three types of hot calendering. Area bonding. In this process, 2, 3 or 4 roller hot metal calendars opposed by specially composed roll can be used depending on the degree of bonding required and the weight of the bat. In this process, as heat is applied from the outside, The inner area is less bonded and becomes more pronounced, that is, with respect to bulky fibrous web. This process is best suited for low to medium weight products requiring light to medium bonding. Major factors influencing this process are roller heat, the roller pressure, the roller speed, and the roller combinations and the cooling temperature of the rolls. Point bonding. This process is mainly used in bonding sanitary napkins, medical products, diapers, etc. It involves the use of two roller nips which may or may not be heated depending on the requirements. The web is fed to the calendar nip. Fibers caught between the engraved point and the smooth roll get adhered together. The degree of bonding depends on the engraved pattern. Bonded areas are tightly compressed and compacted. Embossing. In this process, the heatable metal calendar roll has a male patterned, figured or sculptured roll matching with a female felt roll. The belt calendar. In this process consists of a heated roll and a rubber blanket. Pressure is applied by varying the blanket tension. The products are less bulky compared to hot roll calendar. This process facilitates the use of binders with sharp flowing and melting characteristics. Through air bonding. This process involves the application of hot air through holes positioned below the non-ovens. Vacuum created pulls the air through the open conveyor apron that supports the non-oven as it passes through the oven. Products are generally open, bulky, strong, absorbent, and extensible. Ultrasound bonding. This method is frequently used for patterned or spot bonding. The process involves application of quickly altering compressive forces to localized areas of the web. The compressive forces is converted to thermal energy, which softens the fiber, and upon removal, the softened fiber solidify, forming the bonding. This method is used to make patterned quilts, outdoor jackets, etc. The radiant heat bonding. In this process, the fibrous web is exposed to a source of radiant energy from infrared range, which increases its temperature and melts the binder fibers. Upon removal of the radiant heat source, bonding occurs. Then we'll go on to the next technique of fiber bonding. That's the chemical bonding process. Bonding a web by means of a chemical followed by curing is one of the most common methods of bonding. Chemical binders, adhesive materials are applied to the non-woven fibrous web in different ways. These chemical binders form an adhesive film between the fiber intersections, thereby holding the fibers together. The chemical composition of the binder material determines the strength, stiffness or softness properties, elasticity, water affinity, aging, and durability. Chemical binders are applied in the range from 5 to 60% on the weight of the web. Vinyl polymers, acrylic esters, natural and synthetic rubber, starch are usually used polymer binders applied in aqueous dispersion. Latex are extensively used because they are versatile, economical, easily applied, and effective adhesives. Some of the most common techniques of applying binders to fibrous webs are by saturation, foam spray, and print method. Now, saturation process. Saturation bonding can be carried out in 3 ways using screen, dip squeeze, and size press. Screen saturation is used for intermediate weight non-wovens such as interlinings. Dip squeeze saturation involves complete immersion of the fibrous non-woven web in a trough containing binder and the excess removal by the pair of nip rollers. The binder pickup by the non-woven depends on the weight of non-woven, the dwell time, the nip pressure, and fiber wettability. This method provides higher binder to fiber bonding throughout and is more suitable for lightweight, highly permeable non-wovens. Size press saturation is used in high-speed process such as wet laid non-wovens. Foam binding process. In this process, mechanically generated foam is used to carry the dilute binder to remain at the surface or made to penetrate through the fabric cross-section. Main advantage of the process is more efficient drying and ability to control fabric softness. The concept employed involves applying binder at low water level and high binder solid concentration. Foam bonded non-woven requires less energy to dry the web. Foam bonded non-wovens exhibit enhanced loft resiliency and hand. The spray bonding process. In this process, the binder is sprayed onto the moving web through a system of nozzles strategically mounted on the machine. The depth of penetration of binder depends on the permeability of the web, fiber wettability, and amount of binder. The binder is atomized by air pressure, centrifugal pressure, or hydraulic pressure, and applied on the upper surface of the web as fine droplets. After each spraying, the web is passed through the dryer to remove excess water. This process is best suited to produce bulky, porous non-wovens, as the fibrous web is not compressed. We go on to the next technique, that is the print bonding process. In this process, the binder is applied to the fibrous web only in predetermined area as per the print pattern. The binder is transferred from the feed roller to the engraved roller, and as the web passes the engraved roller, transferring the binder to the fibrous web. The excess binder is removed by doctor blade. The web is further cured for cross-linking the binder. This method is suitable for applying low levels of binder to produce non-wovens suitable for applications that require a part of the fabric to remain binder free. The main advantage of this process is the outstanding softness and adequate strength. The next method is the powder bonding. In this method, the adhesive powder is applied on the fibrous web by heat and pressure. Low glass transition temperature and low molecular weight polyesters and polyolefins are used as powder binders. Bulky and dense non-wovens are produced by this method. Applications. Chemical bonding process. Developed non-wovens find applications in footwear, automotive, home furnishings, wipes, interlinings, medical products, towels, coating substrates, bedding products, furniture applications, apparel, pillows, etc. Non-woven fabrics similar to the regular woven and knitted fabrics are finished to develop certain advantageous properties depending on their end use. Mechanical, chemical, or both finishing techniques can be incorporated to impart certain aesthetic and functional characteristics to the non-wovens. Now, finishing of the non-woven. Non-woven fabrics, similar to the regular woven and knitted fabrics, are finished to develop certain advantageous properties depending on their end use. Mechanical, chemical, or both finishing techniques can be incorporated to impart certain aesthetic and functional characteristics to the non-wovens. Summing up the modules on the non-wovens, I think we have seen the different fiber formation techniques, then the different methods of web formation, and the different bonding techniques used for the consolidation of the non-wovens, and some of the finishing techniques. In this module, we have seen in detail the different mechanical, chemical, and thermal bonding techniques which are used in consolidation of non-wovens for different applications as shown. Thank you.